Me too, yeah. Okay. What now? Okay. I just got recording 1, 3, 2.
Yeah. Hi, welcome everybody. My name is Dr. Roger Marston. I work in the Surreal College of Business, and I'm the president of the Auburn Astronomical Society for about another 4 years. I'm sorry, not Auburn. I wasn't here there. Troy Astronomical Society for about another 5 minutes. And I apologize for missing the last meeting. Those of you who know me as a faculty member know that my wife has had some medical issues and such that she was forced into retirement back in May. Not going to get into all the gory detail, but for a while I've not been able to leave very far from home. She's okay. When you look at her, you never know she's been sick, but she has, one of the issues she has is intermittent debilitating fatigue. It's one of the long COVID symptoms. She'll be fine and go, I'm going to lay down. And she's unconscious for 4 hours. She's out cold. So she's had surgery on her foot. She can't stand for very long. She has vocal cord dysfunction from COVID. So she can't talk very much and she doesn't have much of a voice. And she can't lecture. As an English professor, 5 days a week, Mike, he gets it. They were in the same department. She had to leave. So anyway, point is, it's right now, it's not that it's inconvenient, but when you have to set life priorities, a club has to go below work church life. So I couldn't be here. And what I'm going to do, and I'm going to just say a couple of quick things as president, and then I'm going to step down and give an immediate resignation in a minute as club president. Now, because Justin Robinson, Dr. Robinson, who's a professional astronomer, is the club's vice president, he automatically, immediately becomes club president. We don't have someone taking notes tonight. Dr. Becker, can you make a note or two, just to pass to Roger Howard, please? All right, so first thing, there's some reasons I need to step down as president. One is my wife. 2, you faculty members, you know that they've changed how we count our service and our duties at the university. Oh, yeah. We collect points. And everything we do, service of community, service in the university, teaching, research, all counts points. This club does nothing for me, which is okay. I would do the club, putting brother issues for that. However, it's community service for these 2 guys. Because this is in field for them. For me, in field is me working with the Selma District Attorney to develop strategic plans for their office, some local businesses. And that's what I'm doing for my public service. These guys work with Govind Menon, who's also a member. Dr. Menon is their department chair. Her boss, she's their department secretary. For them, this counts more than just being a fun club. Okay? So, with that said, I'm going to apologize again for having to step aside, but I want to call to the club's attention, you older members who were here before, Eddie, others, remind you that in January, we need to have elections for club officers. So I'm actually going to miss last meeting, this one, and maybe one more, because I think we're probably going to do one for December. So this club's meeting and one more. I'm going to go into stepping aside, making sure that he knows, and these guys know, I'm nominating him to be a longer than a few months replacement for me. The reason for this, when I step down, I'm going to have to take my name off of the club bank account with our club secretary, treasurer, and with Dr. Minnick. And over at, I think it's Bank of Troy is where it is. I'm not sure. Anyway, my name's got to come off. His has got to go on. We don't want to have to do that paperwork too often, right? So I encourage the club, guys, welcome. You're going to have a ball. As the winter gets, as we get through winter and we get started in the early spring, there'll be a lot more to see on the sky. The skies typically are more clear, or clearer, or clearer in the midwinter. I'm sorry?
That's the English professor.
No, he'll tell me. It's okay. I don't want to lecture. Clear? So there'll be a lot to look at. It's one of the banes of an astronomy club is trying to schedule stargate coaching, especially on a campus when we have some challenges. Eddie, were you in the observation committee? Okay, Eddie, you still are. Unless you resign, you still are. And I think you may have been in the observation committee, so I'm gonna take your place in that. That's all right. Any objections? We have an observation committee. The observation committee is charged with two things. Kind of coordinating stargazes and trying to find a place to have them. Okay, now we have a problem. There isn't anywhere around here. The best dark skies we have are in her backyard or front yard, but she's a long way away. Okay, and we have a lot of club members living in Montgomery, and you're in the wrong direction. So we're going to need a volunteer. Be thinking about it to serve, a volunteer opportunity to serve on the observation committee.
I'll send out information to everybody's email and on Facebook about all the committees, so that if you're interested, you can see which one entails what, and if you're interested, we'll have everything coordinated in January.
Yeah, so what I'm hoping to do is in January, when we get rolling again, I'm going to take the observation committee, or the observation committee will take me, whatever. And we have to sit down and start figuring out someplace we can have stargazes where the skies are a little darker. At least probably 3-4 miles away from here. So that's one thing we have to do. Get my name off the checking account, Justin on it is another one. Dr. Banker, you're going to be looking at, we still have an ongoing relationship with the Boy Scouts. Okay, so we need to fire an email and follow the Boy Scouts, which is us helping them with their observing, and also with the, forgive me, Astronomical League. How many of you are actually already club members? How many of you are thinking about it? Okay, great. And I'm going to say this and then I'm going to step down. It's a few minutes to turn the clock. All right, so here's the thing. We have two groups. The Astronomical Society is a club. Membership is dues. It's like, what, $12 a year, $1 a month. Pay about a year. That gets you in the Astronomical League, which has observing programs, lots of benefits, lots of fun stuff. If you don't want to pay the dues, that's cool. You sign up if you're a student, pay through doctorate, you can join the student auxiliary. You get all the benefits of being a full-blown club member, you just don't pay dues, and you're not in the Astronomical League. So what's that? Jacob, you can do either one.
He's a member.
He's a paid-up member, good for you. All right, now, the only other thing is, I'm saying this for Jacob's sake, and you should know this, you cannot be an officer by Alabama law until you're, I think it's 19, so it's not our fault.
Got a long way.
Because to be a corporate officer in this state, you have to be not a minor. So that said, any objections to me stepping aside? Good, I'm not giving you a chance to say no. Justin, you're president, all right?
Thank you very much.
Eddie, we'll chat. And I'm gonna send the back of something to drink, let them have it. Thank y'all for listening.
That mood lighting up? Good evening, everybody. Hope you're doing okay. We are going to do the same kind of format as we did last meeting, where I'm going to give about 5 minutes of some recent space news. And then we're going to talk about my favorite topic, not just of astronomy, but just period, supermassive black holes. Okay. So what has happened recently in space? Well, Mars has been through some tough times. Something smashed into Mars. That's the impact. Does anybody have an idea as to what all this fragmented stuff is? Ooh, ice.
Yeah.
It's ice. It excavated boulders worth of ice. So the InSight lander, back in December of 2021, the InSight lander felt a magnitude 4 Mars quake. It's not on Earth, right? So it's a Mars quake. Detected that, but it was not where the impact site was. It was somewhere else on Mars. It later rolled up to it, literally rolled up to it, and discovered one of the largest craters that ever has been witnessed to happen in real time in the solar system. That thing sent boulder-sized ice out from underneath the lithosphere of Mars, out everywhere. To give you some scale, the crater is 400 feet wide. That's a big impact.
Question,
Yeah.
Is this crater bigger than the one we created when we bombed the moon?
I think so, yeah. Yeah. Turns out nature can do a way better job than we can. So, here's a better picture. So not only was it almost pristine looking, but look at all of this coming out of here. So, other than Mars getting abused by its neighbors, We also have, of course, more James Webb Space Telescope images. So, yeah,
So they asked how big that was. So I just looked it up. So a football field, 300 feet.
yes,
So
that's
for the
football.
little one,
So, yeah,
it's
so
bigger than a football.
to walk across this would be walking across an entire football. Yes.
Almost, yeah, almost.
A quick question.
Yeah, go ahead.
For, I guess for Dr. Banker, what bomb moon, what bomb moon?
Oh, well,
What kind of bomb did we
it's hard
use
to
on
excavate stuff, especially when you have to get a lander there, and it's a lot of trouble to like land stuff on. It's really easy to bomb stuff. So we just bombed the moon and just.
What kind of bomb?
Yeah, what kind of bomb? I think it was just a kinetic device. I don't think it was actually explosive.
Kinetic device, little
TNT.
TNT.
They didn't contaminate
like
the
Minecraft.
results. They didn't want
Sure.
chemical,
It was like a
Yeah, but basically, they wanted to do this and then study the ejecta, what's under the surface of the moon.
Okay.
Send something super fast to the surface.
Can we go to the next slide, Professor, for just a second? I think the one on the right would make a great tie-dye T-shirt for the.
That would. All right.
Awesome.
And then, of course, it seems almost every day at the James Webb Space Telescope, yes.
You go back one slide, I got a question.
Okay.
I was so-
Rhetorical questions, but this is legitimate. How do scientists, because I really don't know, how do scientists know that the stuff, the ice are seeing in the ejecta is not from the impact body instead of Mars? In other words, could it have been like an icy comet or an ice, or
The impactor is driven underground.
Yeah.
It scoops out stuff and hits. The stuff that looks in the radial pattern is from the ejecta. The thing itself, it's like a bullet hitting the ground. It's lodged in there.
Yeah.
Okay. Any other only legitimate questions? That was a legitimate question. So, it seems that every day, the James Webb Space Telescope has been astounding us with its recent images. I know a lot of people, I have a lot of friends at the Space Telescope Science Institute. So the first image where everything looked as it should have was great news because all my friends still have jobs, which is always good. So last time I showed you a comparison between some Hubble Space Telescope images and James Webb. That was a unique little program that some scientists created. We haven't done that yet for these new images, but the Pillars of Creation is one of the most famous nebulas in the Milky Way, and so it turned its sights to that. Every one of these little tiny flashlights is a different star. So here is a comparison between the famous Hubble image and James Webb. James Webb is an infrared telescope. Infrared light has an easier time going through clouds of dust and gas like this whole entire structure is. And so we're able to it's sort of like X-ray vision, except it's with infrared. We're able to see through the gas and see way more stars than we ever were able to see just with the Hubble Space Telescope. Now, James Webb also has multiple cameras and instruments attached to its structure. So this image is taken by what's called NIRCam, which is the near infrared camera. However, it switched to a different instrument and took an image of the same sort of structure, the same place in the sky, except it's with a mid-infrared tool. So if we instead look, not just in the near infrared, which is just out of sight from what our eyes can detect, if we go deeper into the infrared, here is what it looks like. Way different. Just shift a couple of wavelengths, just shift a couple of different energy levels down, and you get this. Now, the important thing to keep in mind is that James Webb is infrared. Infrared is not light that we can detect with our eyes. And these colors are not the actual colors that you would go and see if you were to look at this with your eyes. Yes.
Can you give us some scale to the image real quick? How big is
Oh,
it?
yeah.
Is what? I mean, it's at least on the order of hundreds of light years in size.
Right, I'm saying, those little nodules are maybe solar systems. I'm saying.
Oh, basically, yeah. So every single little speck inside here is a sun-like star, most likely with planets going around it. So miniature solar systems found around almost every star in this nebula. This is what we call stellar nurseries. It is literally a birthplace of many, many, many stars. And most of the time, we're pretty sure, all of the materials that aren't used to create the star are used to create planets. That's one of the bigger jobs of James Webb, is to study exoplanets, planets that are moving around a star that's not our sun. A couple of months ago, James Webb detected the first detection of carbon dioxide in an atmosphere that's not in the solar system. So it's already done more work than most exoplanet studies, and it just started looking at things. So that's in recent space news. Tune in next time, same bat time, same bat place for more space news. But let's get on to the main events. So who knows what this image is? It's a black hole. Is it a black hole?
Oh, no.
It's a picture of a donut, still off Google.
Yeah, exactly. And it's even glazed too. It's very nice. No, that is technically a picture of a black hole. It's mostly the things that are lighting up are the accretion disk around a black hole. Now let's get one thing out of the way. Who has seen Interstellar?
What is that?
Less people than I want, but that's good. So, the black hole in that movie, that black hole had an accretion disk around it. It was like Saturn's rings around the black hole, and then you got some cool lensing effects that happened depending on where they were around it. So black holes that are actively feeding on stuff have a disk around them, and this is what we imaged. This is one of the only two real images of black holes that we have. Every other image of a black hole that you've seen has either been an artist rendition or it's been a computer simulation, like Interstellar was. That was just a computer simulation. This is one of the two only real images of black holes that we have. The other one is where? Ours. Yeah. So I'm going to go through and explain what's going on in this image, and then we'll turn our focus into the black hole in the center of the Milky Way galaxy. Okay? So, first off, because I have some of my students in here, but I have some students that I haven't seen before. So let's start from the basics. What is space-time? What is it? How does it work? Anybody? Is it a vacuum? Is it just nothingness? Or has anybody seen those videos where they take a tarp of rubber or something like that and they put like heavily weighted things in it?
Bowling ball and trampoline.
Exactly. Put a bowling ball and a trampoline. Space-time is a three-dimensional blanket that can be, yeah, four-dimensional, yeah. So, three dimensions in space, one dimension in time. It's a big blanket. It's a big fabric that can be bent and dented and warped by things with mass. Everybody in this room has mass. You're bending space-time right now. The Earth makes a big enough dent in space-time that our moon follows along the curves that the Earth's mass has created. The sun makes a big enough dent in space-time that all the planets of the solar system move around the curve that it has created in space. So, light also has to follow along these curves. Think about space-time as a road, and then think about the worst road that you've ever driven on. Potholes upon potholes upon potholes, right? So if you are driving down that road, you really don't have a choice unless you want to swerve everywhere, right? You got to go through the road. You got to go through the potholes. The same kind of thing happens with things traveling in space and light. Light traverses through space. So if there is a dent or a pivot in the road, the light rays, the path of light has to follow along those things. Anybody ever see these videos, or has anybody ever done this, of like coins in a little spout? That's the exact same thing that's happening. This bend, the reason why everything is moving around and falling in is because there's a big dent here. There's a curve in the path that those quarters and coins are taking. That's the exact same thing that happens when you have something that has a lot of mass and you put it in space. It makes a huge dent, and everything around it follows along the curve in the dent that it just made. We observe this happening all the time. Closer to the sun is closer to the gigantic dent in space that the sun is making, and so light will take an off-ramp off of the freeway. So when we see stars that are very near the sun, we see this dual star thing, where this star is actually where it's supposed to be. It's traveling along. It turns because of the sun's gravity. And when we try and trace back where we think the star was, we get something that looks like this. Light gets bent from things that have a lot of mass. And if you're farther away from the sun, that's not as apparent. And if you're far enough away from the sun, there's nothing to interrupt the light's path, and so it can travel in a straight line just fine. So knowing that, how do you actually make a black hole? Well, what if I just took a blob of mass and started experimenting with it and see if I can make a black hole? The important thing to keep in mind is not only that space-time is a fabric that can be bent, but another thing is this term called escape velocity. Escape velocity just means how far or how fast you need to travel in order to completely get away from something's gravity. right? If I try and make myself move fast like this, clearly that wasn't enough speed for me to launch myself out of the atmosphere, right? But how fast do rockets have to travel?
1,000
Miles per hour.
miles per
Yep.
hour to leave Earth.
Come on in, to leave Earth. Yeah. Rockets, every single rocket that's ever left the surface of the Earth has had to travel at least 30-something thousand miles per hour in order to leave the surface of the Earth. Any speed that was less than that, they wouldn't have left. They would have been dragged back down by the Earth's gravity. So, let's say I have some blob of mass. Any blob of mass, doesn't matter what it's made of. And I'm not going to change the amount of mass that I use. The only thing that I'm going to do is I'm going to take all of that mass and I'm going to start squishing it down. And I want to see what effect that has on escape velocity. So this little arrow is either going to shrink or expand. If it expands, that means that the speed at which you need to go to get away from this blob has to be faster. And if it shrinks, that means that the speed at which you need to go is going to be shorter. So if I took this mass and I compressed it, do you think that I would have to move faster or slower to get away from it after I started messing? Faster. Why is that?
Because you're much closer to the center of the mass.
You're much closer to the center of mass. So what have I done to this thing? I've taken the same amount of mass and I put it in a smaller volume. What have I changed?
You change the distance from the center of mass.
Yes.
Well,
Think more simply.
radius.
The density. The density. More dense things have a higher gravitational pull. If something has a higher gravitational pull, that means it's harder to get away from it. So if I shrink this thing, the escape velocity goes up. I have to work harder to get away from this thing. I haven't changed the mass at all. All I've done is make it a little denser. So what happens if I just keep increasing the density? Just squish it more. The escape velocity goes up. If I squish it more, the escape velocity goes up. What if I just do this infinite? What happens? Nuts, right? Take any mass that you want. If you crush it down significantly enough, then the speed at which you need to go to get away from it is faster than the speed at which light moves. It gets faster than the speed of light. So anytime that you read a news article or something that's put in the Times or whatever, and every single time that they mention a black hole, it's immediately followed by something so massive that not even every single time. And it's that same wording too. Different writers, same phrase. It drives me nuts because they never explain why or how that works. This is why. The thing that gets denser and denser and denser, it's harder to get away from it. So that's why when people explain what a black hole is, they say it's so heavy that not even light can escape. It's because that object that you've created is so dense that the speed at which you need to go to get away from it is faster than light. In other words, nothing's fast enough. Because the speed of light is the speed limit of the universe. Nothing can go faster. Okay. So, what did I just make? I took all of that mass and I put it into a point smaller than you could see in a microscope. So what kind of matter, what kind of object did I just make?
A black hole.
A black hole. That's exactly right. That's exactly right. But all of the stuff that I started with, all that blob is in that point. I've made it bigger so you can see it, but that point's smaller, right? So what happens around it? I told you that the escape velocity near this object is greater than the speed of light. So go ahead.
So does that mean that if we assume that the thing we're doing physics on is a point mass, then it's a black hole?
Yeah, basically.
So should we not then assume that every single problem is a point mass for the
I mean,
sake of
You
convenience?
can if it's spherical. Yeah. Yeah, you can actually prove that. So, if there is a region around this place where the speed at which you need to go is faster than light, well, then there must be some place where you can be sufficiently far enough so that you don't have to worry about them. Right? We get far enough away from something, we stop feeling the gravity. So, who's heard of the term event horizon? Or seen the movie Event Horizon?
Yeah, right.
The event horizon is simply the boundary in space. There is a limited volume of space around this point, this blob, where the speed at which you need to go is faster than light. If you move past that barrier, then light can escape. We can see it. If you're traveling sufficiently fast enough, you can get away. So this little boundary that I just made here, this circle, is the volume around this thing where you have to go faster than light to escape. So nothing can escape. Photons, particles of light are literally dragged back in because they're not moving fast enough to leave. And then everything outside of that, right, the speed of light is fast enough to go. So black holes don't have a surface. They're not gigantic black spheres in space where if you go up to one, you can slap it, right? You can't. There is no surface. There is nothing to touch. What it is, yeah,
So another weird fact about that boundary.
sure.
As you cross that boundary, the definition of time and space flip.
Yep.
Was that-
Time moves slower as you get closer to a black hole than it does for someone else who's safe and far away.
Excuse me.
Yeah.
Isn't it, you said that, but you framed that in that it's a black hole, but isn't that true on any
Yes,
amount of matter?
yes,
Your time passes more slowly as you go towards a larger condensation or collection of matter.
yes,
So time passes slower on Jupiter
yes, it does.
than Earth, than the moon.
The people, the astronauts on the International Space Station are, by definition, time travelers. Because they're far away from Earth. They're in orbit around Earth, which means that they're farther away from Earth's gravity than we are, which means that we are moving through time slower than the astronauts on the International Space Station. Time travel. Yeah. Mhm. So, what is this boundary called? It's called the event horizon. Because no events can be observed if it goes past that point. Anything that we've ever observed in space, in anything, you're doing it right now with your eyes. The only time that you can see something or detect something is if a photon arrives at your detector or your face detectors, your eyeballs, right? So the event horizon describes where photons can no longer travel, which means that we can't detect them no matter where we are. And the size of this thing, the size between where all that mass is in the center and the event horizon, that's called the Schwarzschild radius. Carl Schwarzschild was one of the first people to start messing around with Einstein's equations after he made them. And he figured out you can calculate how big a black hole is just by measuring how massive it is. So we name it after him.
He did it in the trenches of World War I.
He did it in the trenches of World War I. So very, very calm environment. So what would we see? That's all great. What would we actually see? If we actually took a blob, we crushed it down, we made a black hole, we understand everything about it, what would we see?
Can you just show us this?
Yeah.
In the,
Yeah, nothing.
Nothing, right?
Like Kansas Davis.
Yeah,
no, when you showed Virgo A star, which was this M87, the dark spot in the middle
yeah.
would be the end of that. would be the
Oh, I'm
event
working
horizon.
towards it.
Okay.
Don't spoil the movie for everyone else. So that's, lame, right? Black holes don't emit light. When I say they don't emit light, I mean photons can't get out of them. So they look black because literally photons can't leave, and so we can't detect them. So I'm a black hole scientist. How in the world do I study black holes if we can't get any light from them? Everything else. We look at everything else. We look at their effect that they have on the environment around them. So let's take this for example. I totally didn't make this in Microsoft Paint, I promise. Let's pretend we have a black hole somewhere in here. I don't know how big it is. I don't know how massive it is. I don't even know if there's one there. We're just going to see. Okay? Let's pretend all of this stuff is gas. Think of any gas you want. Hydrogen, helium, sulfur, whatever. It doesn't matter. So, if something is rotating sufficiently close to a black hole, we can use that stuff to tell us everything that we would want to know or possibly could know about a black hole. So, the important thing is that we can only detect photons that are in what we call stable orbits, meaning they are repeating their motions for a sufficiently long amount of time so that us little tiny ants on Earth can detect them from our telescopes. Photons have to travel to us and get here in order for us to see them. If they fall into the black hole, that sucks, right? So a stable orbit, like if you ignore the fact that the moon is slightly edging away from us by like an inch every decade or so, or something like that, something crazy.
It's not a centimeter a century.
Centimeter century, so that's, yeah, I was off by a couple orders of magnitude. The moon's orbit is pretty stable. It's been doing it for a very long period of time. Our orbit around the sun is very stable. We've been doing the same thing for a long period of time. Yeah.
The only question I have is, what happens if it gets sunk in a black hole?
Ah, well, we created a word for that.
Oh, I
You want to say it?
know. It's a cool word, dude.
Oh, you say it.
Oh, it's spaghettification.
There you go.
It's amazing. It's a very Italian name.
Isn't it? Yeah, every time I teach the vocab word, I have to. Yeah.
It is just the coolest science.
You won't see it.
It really is.
Nobody will see it.
Exactly.
Although,
Spaghettification.
that's right.
Spaghetti balls.
Wait,
So,
Might take a shot at explaining.
go for it.
When you get close enough to a high enough gravity, the pull on one side of your body is more than the pull on the other side for the centrifugal force keeping you away. So it starts to rip you apart and pull you out, just like rolling pasta, into long streams of matter.
You seem way too happy about this.
And the experiment is spaghettification. It draws you into long streams of matter that look like spaghetti.
It's a title for it. It's just the extreme version of the same thing that causes times.
Yeah, and it's a more dramatic version of what happens to you guys every day. You're taller when you're sleeping than you are when you're standing up during the day.
Oh my God, sleep the rest of my life.
Yeah, because what direction does gravity point? Where's down in space?
Sorry.
Towards the center.
Yeah.
Towards in. It points in, right? From our perspective, sure, it points down. So gravity's pulling down on you this entire time, and so for a long period of time, gravity will do this to you. And then you lay down horizontal on the bed, you're no longer being pulled from your head down. It's evenly spread on your whole body, pulling you down. And so you stretch back out. Test it. Test me. Measure your height at the end of the day before you go to bed, and then measure your height in the morning. You will be taller, I promise you. It might be like, half an inch. But anyways, yeah.
Are you saying like it's taller than
Yeah. Yeah.
Why can we do that?
Sometime in the future. Okay.
Well, astronauts
So-
actually do that when they're in orbit in the space station for a long period of time. And then they come back to Earth. Their height is different.
Mhm.
A lot. I mean, a little more than just a fraction. It's a pretty good amount.
So much for that hurts their joints.
Yeah, it does. Their joints aren't used to having their joints filled with fluid. It's a mess. It's ugly.
All right. Back to Michael.
You got to admit, this spaghettification is a cool
Oh,
trick.
yeah, absolutely. So if you are sufficiently far away from a black hole, but still experiencing its gravity pretty strongly, the stuff that keeps repeating its patterns are in a stable orbit. However, if things are closer to the black hole, they can't keep completing their orbit, and so eventually they will spiral inwards. Spiraling inwards means that we can't detect them. That'll be an unstable orbit. We can't see that. So the problem here is that we see this gas. We don't see light coming from this gas. So there is a limit to how close things can be to a black hole that we can still see. Who here ever read the term shadow of the black hole when the black hole image first came out? No? Okay, good, because it annoys me to no end. They all talked about the shadow of the black hole as if it were a phrase that every black hole scientist and astronomer used. Not a single person that I know has ever used that phrase, okay? The shadow that they were trying to describe is that the center of that glazed donut that I had in the front slide, that center is not the black hole, because all the light that we detected came from gas that's moving in stable orbits. That's farther away from the black hole. So you can see this gas really doesn't trace the black hole, but this photon, if we were able to detect it, that kind of traces out the size. You guys kind of see that? So black holes, the black hole in that image is smaller than that hole. And the reason for that is because we can't detect the gas that gets too close. So it's a shadow. It's a black hole plus a shadow. Do black holes cast shadows? They don't. But anyways, if you ever come across that phrase, that's what they mean. And I'm loving having to take up the mantle of explaining it because no journal article writer that I've ever read has explained it. Yeah.
So if the black hole sees its shadow, do we get any more?
Just that question, yeah, go ahead.
What is the term, just so everybody knows, it's not black hole shadow, what is the term for that?
The innermost circular orbit. Yes, Joe, yeah.
Does
Okay.
it- Does the black hole always remain permanent? I mean, does it travel? Does it move?
Oh, yeah. You're moving right now, aren't you?
Yeah.
Yeah. The Earth is rotating on its axis, and it's also traveling around the sun. That's also dragging all the planets around the center of the Milky Way. That's also infalling with all the other galaxies around us towards the Virgo supercluster of galaxies. So yes, black holes are moving.
You have black holes
And spinning.
binary systems where they orbit around other black holes, or even other stars.
Uh-huh. Yep.
So if we were like, dead, we'll still be moving.
If we were, what?
If we were dead laying down, Will we still be able to move?
Your body would, yeah.
You're still,
Yep.
Earth is still moving.
Yeah, but you're not.
Well, no, but you
In
are.
the grand scheme of things, the sun is pulling the planets of the solar system along its path as it moves around the supermassive black hole at the center of the Milky Way at roughly, 3 to 400,000 miles per hour, somewhere around there. 300 kilometers per second, like that. Yeah. All right. So the other important thing to keep in mind, we're going to piece together the image before we return to the image, and so we have all the context before we look at it again. Okay. So not only can gas orbit in only certain places around a black hole, but black holes make gigantic dents in space-time, and light has to follow along any of those dents or potholes that are created by things with mass. So let's pretend that I have a disk of gas around a black hole, like Saturn's rings. Let's pretend I have Saturn's rings around a black hole. That means that there's part of the disk that's close to us, and part of the disk that's hidden behind the black hole, right? This isn't really what we see, because all the light that's coming from the gas behind has to travel to us, and it smacks right into that dent that the black hole is making. When you make a sufficiently big dent in space-time like that, it literally acts like a lens that we have here on Earth. It bends light. It creates distorted images. So the light that's coming from behind the black hole, part of the disk that's behind the black hole, some of that light is going to get bent up and around the North Pole, and some of it is going to get bent down and around the South Pole. So this is not what we would see if we went and looked at this black hole in person. What we would see is probably something that looks like this. Looks familiar to anybody?
Yes.
Am I giving you Interstellar vibes? This is why the black hole in Interstellar looks the way that it does. It's the exact same reason. There is a disk of material around the black hole. The part that's behind gets lens up above and down below. This stuff, this right here, that's not the real disk. The real disk is the part that's cutting across the equator here. This stuff is just light that came from behind the black hole, that part of the disk, which is real, and it just got bent. It took an off-ramp on its way to get to us. Yeah.
For the movie, this is not an artist rendition.
Nope. This is the equations that govern black holes. It's the theory of relativity equations of the computer. That's math,
So
ladies and gents.
For the movie, they actually did a real simulation.
I'm so glad. That's a wonderful segue. One of my favorite stories is that, or one of my favorite things to say is that if you give scientists money, they will give you cool things. We have made simulations of black holes. However, when you make a simulation, you have to decide how detailed you want it to be. What's your resolution? If you, let's say you buy an HD 4K TV, right? That's going to be more expensive than one of those old TVs that sat around, right? More pixels. It's harder to do. So if you say, I want a lot of pixels, well, then you're going to need a lot of computing power, which requires a lot of money. Some scientists have a lot of money. Most scientists don't, right? So there's a limit. There's a limit in how detailed our simulations can be. Christopher Nolan, who's directed Interstellar, didn't know anything about that. And so he's just like, I want to make a really cool simulation. So he went to scientists, and Kip Thorne, who was one of the scientific, not contributor, scientific consultant on the movie. And Christopher Nolan said, okay, I know you guys run black hole simulations. I don't know how much that costs, but if I give you like, I don't know, $100 million, could you make a detailed image? And they're like, yeah, we can. So this was so revolutionary that it actually warranted a scientific paper that got published. And what's hilarious is that in this paper, they have to report what the resolution was, and they had to refer to it as IMAX resolution, which has never been said for any simulation for a science paper that I've ever read in my life. But
The question is, does that now set a standard for future research to use that one simulate, that one resolution?
oh well, yeah.
Sure, next time you give someone $100 million.
Yeah. So every once in a while, Hollywood does something cool. Every once in a while. Anyway, so there's one last piece that we need in order to kind of match what that image was that I showed you at the beginning of the presentation. So we've got the lensing part down. We've got this weird halo thing going on. But the last thing is something called the Doppler effect. Who's heard of the Doppler effect? My students better raise their hands. So as light moves towards you, it looks more energetic. Every photon, every particle of light has a wavelength, And that wavelength determines its color. Really long wavelengths look red, really short wavelengths look blue. So when something is moving towards you, imagine standing on the side of the road and a car is coming towards you and then goes away from you. What does that sound like? Right? The pitch changes. Is the engine, the thing that's producing the sound, is that changing the sound that it produces at all?
No.
No. The reason that you hear a different pitch is because part of the journey, the car is coming towards you, so the sound waves that are being emitted get compressed on their way to you, so you hear more sound per second, so the pitch goes up. And then when the car is going away from you, those sound waves stretch out, you hear less sound per second, the pitch goes down. The same exact thing happens with light. If something is coming towards you sufficiently fast, all of those wavelengths get compressed and the color shifts to bluer colors on Roy G. Biv on the color spectrum.
So if the light's red, it's gotta go fast.
Yes, exactly. And when it's going away from you, everything is stretched out, and so things look more red. So light that's coming towards you looks more energetic. It's going to be bluer colors. So if this thing is rotating, like everything in the universe is rotating, let's say it's moving like this. That means that if it's moving like this, and you do a snapshot, one part of the disk, see how often this comes up? One part of the disk always looks like it's coming towards you. All of that light always looks like it's coming towards you. And then on this side of the disk, all of that light looks like it's going away from us. So this part of the disk is going to appear to be a more energetic color, and this side is going to look like a less energetic color. So what we would see is not something that looks like this, it would probably be something that looks like that. Thank you, I was very proud of that animation. Okay, I think we have all the keys. Okay, I think we have all the keys in order to actually what we call diagnose, right? We run diagnostics on things. We want to take an image and we want to dissect it and figure out everything that we can ever learn just from that one image of the black hole that we got. Okay, so where is that black hole? The one that I just showed at the beginning of the presentation, where is it? The center of Messier 87, which is a gigantic elliptical galaxy that's more than 55 million light years away from Earth. Here it is. That's the galaxy. This whole thing is the galaxy. And this thing is a jet of highly energetic plasma that has been accelerated to nearly the speed of light because it was very close to this black hole, it narrowly missed, and it got shot back out into space in a path that's really, really close to hitting Earth. It's not, but it's close. So this is our target. Inside the core of that galaxy, inside its nucleus, is a supermassive black hole that's doing some cool things. So when we started observing and trying to get an image of the black hole, we wanted to run a couple of simulations and get an idea, a sort of gauge as to what to expect. Because if we have something to expect and we get in the ballpark, that makes it easier for us to interpret the image that we get out at the end. So there was some folks over at Frankfurt in Germany that made a simulation of this region, and they tried to make it so that it matched what we expect the environment to look like. So I'll play this real quick. This thing is meant to represent the black hole. This is the accretion disk that's spinning very rapidly. This stuff is stuff that was spiraling in, narrowly missed, and got shot out of the north and south pole of the black hole. Now we can move things around. Things are brighter and yellow as it's getting towards the center because it heats up as you get closer to the black hole because things are moving faster. And we've got to orient it so that the jet is pointing in the same direction that we saw it to be pointing in the first place. It's almost pointing towards Earth. And so it has to be oriented sort of like this. And then this is what the simulation says that the radio telescopes that we use to observe it, this is probably what they would see. In order for the jet to almost be pointing at Earth, the accretion disk of material around the black hole has to be oriented like this. So if we're right, that means that we won't get that interstellar effect because it has to be pointed like this. Some part of the disk has to be behind the black hole in order for you to get that cool lensing. But if this is right, it has to be more like this. Okay? Okay. So what happens, and it's just something that I've finagled, what would happen, because this is a simulation of what the radio telescopes would see, that orange glazed donut that I showed you at the beginning. What would happen if I took this and just pivoted it? What would happen? Well, I hope no one gets nauseous. That's what would happen. It's a lens. It's literally a lens. Are you doing okay?
That's cool.
So, it happened to be be oriented in any other way, we would see the disk in front and we would get that halo stuff at the end. We don't think it's like that. The jet has to be pointing towards us, which means it's got to be oriented like this, not like this. But I couldn't resist. That's so cool. Okay. So here are the actual observations that we got from the Event Horizon Telescope. We turned half of the surface of the globe into a telescope. Sometimes humans do some pretty cool things. This is what they saw. This is 8 different radio telescopes that all worked in synchronous, in tandem with one another. And this is the accretion disk that we saw. And we took multiple images of it over the course of a couple of weeks. And the crazy thing about it is that this disk varies on human timescales. Weeks. Look at this. That's the actual disk. And it's actually moving and it's changing. That's on the scale of weeks. You know how few things in astronomy will change on the course of a human time scale? And by human, I mean like 100 years. Things take millions and millions and millions of years to change. However, if you're close to a black hole, that thing can change on extremely short time scales. Yeah.
So as a tool for finding black holes, that timescales are useful. Because
Yes.
only things that are really small can change on really small timescales.
Yes.
So one of the ways we can tell something is a black hole is if it can change on the scale of weeks. Sometimes we can't see the black holes, like we have to do, special observations to see that. But sometimes when we look at an object, we're not sure if it is a black hole. If we can see that it's changing on an order of years or millennia, the odds are it's pretty small, which means it's probably got to be a black hole.
Yep. So, put it all together. What's going on in this image?
So the accretion disk is that like
Mm-hmm.
diagonal?
No, it's not the diagonal, it's the donut. That's
What's the
accretion
diagonal?
disk. That's just extra flares, extra energy.
The abyss horizon will be the closest part to the ring.
Yes. So this here is all of the gas that's been moving in stable orbits, right? We can't see the stuff that's on unstable orbits and fell in. So this hole in the center is not the black hole. The black hole is somewhere in the center there. And then that empty region is the point of no return. It's where photons can no longer repeat their orbits, and so they fall in, and we can't detect them. It doesn't mean that stuff isn't there. It's just stuff that we haven't been able to detect. Why is the bottom brighter than the top?
Because
Don't worry. No, he raised his hand. Hold on.
Because it's orientated, or it's oriented to where it's not quite as close to us on the top as it is on the bottom.
Exactly. So we know that it has to be pointed like this because of the jet that's almost hitting Earth, right? And this thing is also rotating. The bottom is blue shifted, which means that not only can we tell roughly how big the black hole is and the orientation of the accretion disk, but we can tell the rotation direction. Watch this. If the accretion disk is going this way, and it's got to be facing towards us, but the bottom is blue shifted, this way. That means that the accretion disk has to be tilted ever so slightly towards us, so that by the time the gas comes down here, part of it is pointing towards you, and by the time it gets up here, part of it's going away from you. So the bottom gets an extra boost from blue shift, and the top gets some red shift. So from our perspective, the top looks like it lost some energy, and the bottom looks like it gained some energy. One image, we can tell how big it is, how big is the accretion disk, what is the orientation of the accretion disk, and what direction is it rotating? This thing's 55 million light years away around a black hole. And we turn half the Earth into a telescope in order to see. If it's not being communicated, this is one of the most important achievements of humans, period. And I'm very clearly biased, but I stand by that opinion. Okay.
So, to give everybody, because I'm not sure if the scale is really.
I'll get to it. I'll get to it. So, this is just the more high-res version that I can get because I'm an astronomer. Okay, so here's the size scale. This thing is bigger than the solar system. Look at this. Pluto's orbit only gets out there. Voyager left the solar system a couple of years ago. It can only get to the edge, the inner edge of the accretion disk. This black hole is bigger than our solar system. That's pretty big.
You're saying the black hole is bigger than our solar
The
system.
black hole plus the accretion disk, the
Thank you
whole
very much.
system.
That's all.
Well, I mean, the shadowy, like, look part there, that's the, ISCO, the innermost.
Yeah, no, the reason I said it, because what he said was when you have a black hole that is infinitely small.
Sure, but the event
Oh,
horizon,
so we're
the
talking
Schwarzschild
about-
radius.
He's talking about the black hole mass object, he's talking about the accretion disk.
The black hole plus the
Has a
event horizon
sphere.
plus the accretion, yes.
For a little bit of clarification, like not me, I'm asking.
Sure.
Whenever he said that it would be small, I thought that was just like for conceptualizing, because we don't know the actual size of the black hole, right? We just know that it's.
Yes, we know the actual size.
We do know the actual size.
The size is just, the size of a black hole is just how much volume of space is the speed of light insufficient to get away.
Okay, so we
That's
don't,
the
okay,
size.
that's the size of the black hole.
Yes.
We don't know the size of whatever cosmic.
No.
mass.
We don't know anything that's going on within the.
Okay.
Yes. Great question. Yeah.
A little more, I guess, context. Since it takes, like 8 minutes for light to get here from the
From
sun,
the sun, yeah.
theoretically, ignoring the fact that light can't get out there,
Mhm.
how long would it take for light to get from the center to the, event horizon?
Well, we're one AU away from the sun. The radius of this black hole is 120, so it'll take 120 times 8 minutes.
Wow.
Yeah. You had a question?
Well, you just said to him, that would be the Schwarzschild
Yes.
radius?
Yes.
Is what you're calling.
When I talk about the size of the black hole, I talk about the Schwarzschild
Okay.
radius. Yeah. Okay. Let's go on.
Just. Yeah, I just checked those, confirming, so that black sort of shadowy region, that, we call that the ISCO, that's, it's only a few times, like 2, maybe 3 times the Schwarzschild radius.
Yeah.
The black hole is almost as big as that black region.
Yeah. Yep. Okay. So turning our sights now, I forget who, a couple of people answered it. The second image that we got was of the supermassive black hole at the center of the Milky Way, of our galaxy. So let's talk about that for a little bit. The next observable target is Sagittarius A star. That's the name of our supermassive black hole. What have we done with this black hole since we started to know that it was there? Well, one of the most important stories and one of the most important achievements in astronomy, period, is that we looked in the center of the Milky Way and we started to track and observe and record the orbits of individual stars that were moving around what was back then only believed to be an invisible point. Back, rewind the clock 20, 30 years ago, no one really believed that black holes were real. Einstein didn't even believe that they were real when he made the theory of relativity that directly predicted the existence of black holes. He didn't even think they were.
The first one was the discovery of such.
Exactly. And it wasn't until really when we sent up the Hubble Space Telescope that we figured out that the black holes are indeed real and they have a very important role to play in the universe. So what did we do to prove that there was a black hole there? Well, this team over at UCLA used the Keck telescopes in Hawaii to monitor individual stars. Each one of these little orbs is an individual star in the center of the Milky Way. If anybody was here for Dr. Ravalsky's talk a couple of weeks ago, who also used this animation. So let me play it. This data starts in 1995 and goes through 25 years. All of these are individual stars rocketing around some invisible points. We don't know what's there. We can't see it, right? But what we can do is we can take the information of all these stars' orbits. We can take how big the orbits are, how fast are they moving, and we can put all of that information into a computer and say how much mass needs to be at that invisible star point in order to make all these stars do what they're doing. That result was published not too long ago, and it was calculated that the amount of mass that needs to be there is 4 million times the mass of the sun packed into a volume that's smaller than Mercury's orbit. There is not an object in physics, that's not an object in nature that can fit that description other than a supermassive black hole. And that research was so revolutionary that it won the Nobel Prize in Physics in 2020, or the year that we never talked about it. This is a three-dimensional,
Wait, you have to explain it. Why is it the year you never talk about?
because that's the year of the pandemic.
Oh, that year you never talked about.
That year, yeah. Anywho, this is a three-dimensional map that we made. Here is all of these stars' orbits in the center of the Milky Way. It's a big spherical structure made of millions or billions of stars, all orbiting around the same supermassive black hole. We've learned quite a bit about this black hole, but if we can take a picture, we're gonna take a picture. Yeah.
Justin, just for some clarification, what kind of time scale are those orbits actually on, and therefore,
Years.
how much of them was actually captured?
Most of them were, yeah, it's on the time scale of years to decades. So this yellow one here has the best one here. So starting from 95, and it goes around, it completes half of it in about 7 years. Yeah, 10 to 12 years for the shortest time scales of orbits. Yeah. Okay. So the disk for M87 star, the disk that we've already gotten in 2019, that disk varied on the course of weeks. Sagittarius A star is a much smaller black hole, and it's not an actively feeding one either. It's not given a consistent source of food. So stuff can change on the time scale of minutes. Minutes. You look at it 1 minute and you look back at it, it's going to look completely different. These 4 panels are different simulations that we ran, similar to what we did with M87 star, where we ran a simulation in order for us to get a ballpark, a good idea as to what to expect when we got the image. This is the same kind of thing here, where this is a simulation of radio, so the same kind of light that the M87 picture saw. This is also radio, this is infrared, and this is X-ray. So this is what we expect to be going on around the black hole. It's chaotic. It is stochastic. It's random. There's random flares that go off. This is seconds down here. It's some unit that means seconds. There's going to be a flare that happens here over the course of maybe an hour. Random flare. Just random energy getting ejected because things aren't spiraling in a nice, thinly organized disk. It's just a crazy vortex around this thing. So how do you image something that's changing that rapidly? Well, I mean, we did it, but how do you do something like that? Well, you take images and you keep taking images and you keep taking images. And we know it's not going to look the same from image to image, but what we can do is we can just average them all together and present a conglomerate average view of a week in the lifetime of the supermassive black hole. Okay, so yeah, here it is. This is the image of the supermassive black hole at the center of the Milky Way. This is Sagittarius A star. Now, we can't analyze this in precisely the same way that we can with M87 star, because all of the blue shifting and red shifting in orientation, that assumes that that thing is a disk, and that disk doesn't really change. The rotation speed can change, the slight little flares can change, but it is a disk, and it's been doing disky things for a lot of disky years, right? This isn't a disk. This isn't a disk. So what this is an average of what's been going on in a week of the lifetime of a black hole. This is not blue shift. That's not blue shift. That's not blue shift. What those are random flares that went off and then got taken and put into the average of what's been going on here. This is just one snapshot, one average of 1 week. If we took this again, if we do the exact same thing experiments again, it would look completely different. Yeah.
Does it make much difference observationally, the fact that we're out as one of the arms of the Milky Way?
Not really, because we're looking at radio.
But we're looking edgewise versus M87 where you're looking at that
Oh, yeah.
face on.
Exactly. So it's a little hard. It's not quite apples to apples because again, this isn't a disk, right? So nothing is remaining in the equatorial plane. Nothing is. Yeah, exactly. So M87, yeah. If we were above M87 instead of looking at it face on, then we would see a different image. Here we might see some lensing effects, but then again, it's an average over a lot of random flares and energetic events. So it's not quite the same analysis. So how big is this thing? Well, there's a fun simulation that I found. So here is to scale how big Sagittarius A star is from 27,000 light years away. We're 27,000 light years away from the center of our Milky Way. And that's how big M87 star would be at the correct distance, 55 million light years away. The reason why we chose these two black holes as the first black holes that we wanted to get an image of is because from our perspective, they're the same size on the sky. Ours is smaller but closer, so it looks bigger. M87 star is way bigger, but it's farther away, so it looks smaller. These two things are the exact same size. So what if I took M87 star and pulled it so that it was next to Sagittarius A star? Oh, let's just do it. Play the jaws because a tad bigger, I would say. Sagittarius A star, that black hole, if you took away the sun and put the black hole in the same spot, that black hole wouldn't even touch Mercury. That's how small it is. And even so, it has 4 million times the mass of the sun packed into that volume. Here's another comparison. So this was M87 star, smaller than the black hole in there. This little area, that's ours. And this is the sun size for comparison. Oh, wow. And this is a trace out of Mercury's orbit. So, what are we doing next? I don't actually know, but this is pretty cool. Thank you, everybody. There is a storm coming tonight. It's not a big storm, but there's going to be rain clouds. There was wispy clouds all day today. I have no idea what the cloud cover is now, but how's about we go and try it? Okay?
Let me go take a look, see what it looks like.
Before we break up, though, does anybody have any questions?
Oh, sure.
About black holes, about space in general? Got the trip right there.
Okay, right.
Spell spaghettification.
You spell it?
Yeah.
Spaghetti, chop off the last letter and add vacation at the end.
Okay.
Yep.
I'm sorry, I was reading it.
That's okay. Jacob?
Your drawing of the.
Yes.
It looks like a fast food restaurant
He's been waiting to tell you that.
called Pizza Planet.
Thank you.
You missed your calling and graphic design.
I know, I really did, yeah.
You know,
Yes.
my new
Yeah.
office, the quad.
When we do when we do the paper class,
Oh, yeah.
you'll see that up right each other. You'll see like the intermediate steps. Yeah, right, you said, but if you look at, I'll show you the paper class that is, you can see the individual.
I do want to
images like that. Yeah.
Do we have any more questions? About science, space? All right, let's give Dr. Robinson one more round of applause.
Thank you very much.
Justin,
Yeah.
Moon, Saturn, Jupiter, Vega,